In this screencast, we're going to learn a little bit about linear algebra within SciPy and NumPy and the tools we've been using. This is going to be first introduction, dealing mostly with solving linear systems, and we're going to spend more time in the future working with some of this. Before we get started, though, we should talk about how are we going to store the information about vectors and matrices. Up until now, we've been using arrays for storing things. We are going to continue to do that. The important thing to note is that an array is not a vector, it's not a matrix, and so that this is going to lead to some slight complications or annoyances as we go forward. There is a matrix object, so we could define something that's a matrix. In general, I don't use it because, well, matrices and vectors are actually pretty rare in most things that we do. When we deal with data, for example, we want to deal with them as arrays. So we're going to continue to use arrays and just deal with the consequences of that. In the end, I think it's easier to use arrays than it is to try to use something else and then switch between the two of them and get confused about what each one of them do. Okay, so for this purpose, let's start by defining a vector. And let's use the one that from the example we did in class. So there we were solving a system of equations ax equals b, and we had b was given by 8, 4, 6. So this array that we constructed here is supposed to represent the vector. Okay, so we can type that in. We look at it. Yes, what do you know? It's a three component thing. This represents our vector. Now, we should be a little careful about this. This is a natural way to type it in, but this isn't really quite what we want. For most things that we do, this will work, because behind the scenes, SciPy will magically do the right things. But this isn't right, and we can see that by looking at, for example, what's 1 over b? It's 0. Why did this happen? Well, this happened, again, for the same reason that it always happens. We stored b as an integer. We can see that if we look at the data type or D type of the array, it tells us it's an integer. Why did it do this? Because we entered integers, and so it does the best job it can to store the data in the format that you specify. As I said, this will typically work, but it's not what we want. We really should store it in the format that we mean it to be stored in, and that's floating points. We can do that in a number of ways. The simplest way is just to make any one of these values a floating point by, for example, sticking a dot in. Okay? Doesn't matter which one, don't have to do them all. Now it knows that it can't use an integer to store this entire array, and so it doesn't. It uses a float. And if we calculate 1 over b, we now get the right answer. Okay? So that's a word of warning to you going forward. We need to do this, we need to be careful about this. Okay, for the example in class, we also defined A. A is a matrix, so it's in this case 3 by 3 array, two-dimensional array. We can specify that by hand as shown here. It really is, if you like, an array of arrays, if you want to think of it that way. And so here I've typed it out with a whole bunch of spaces in just to make that clear. These spaces aren't necessary. But we see here, this is the first row, this is the second row, this is the third row of the array, all of the matrix, I mean, all of it's contained inside another pair of square brackets to denote that it's an array of these objects. Okay. And so this will create our two-dimensional array. In case you didn't notice, I did have a decimal point in there, so this will also be stored as floats, and we can see that here because it prints decimal points too. It even shows us that yes, this is the nice 3 by 3 matrix that we had specified before. Okay, so let's keep those and let's load up the module that contains all the goodies. So that's scipy.linalg. Again, I give it a shorthand name. I like to call it LA. Let's look at the documentation. So what do we know is linear algebra? Tells us other things we can look at. So for example, in NumPy itself contains a number of linear algebra functions. So in fact, it isn't really entirely necessary to use SciPy for this purpose, but we're going to anyway. The routines are not exactly the same. Okay, It has, for example, its own inverse function, which behaves slightly differently than this one in the corner cases where checking the inverse is hard. So I'm always going to use this. You can choose not to, but then you'll have to deal with any repercussions of that. For us, we're going to use this now, and so let's look at what we have. We have the basics. We've already mentioned the inverse. Okay. Determinant of a matrix is also something that's important. So it has some of the standard routines. If you've talked about matrices before, you've heard of these things. For us here, we're mostly going to be interested in solve. Okay, because what do you know? It solves a linear system of equations, exactly what we've been talking about. There's also solve banded, which is something that we're going to see in the lab this week. Okay, and then there's other specialized things and a few other things that will be mentioned in the future. Eigenvalues are a big topic that we'll talk about later. Okay, there's also a whole bunch of decompositions. So as briefly mentioned, the LU decomposition is going to be an important thing for us, and we're going to talk about that, or have talked about that in class on Wednesday. So LU factor, and LU solve are going to be the important things. We'll talk about singular value decompositions and probably not talk about the rest of them, but again, there's other useful decompositions in here. Okay. There's also some other matrix functions which we're not going to talk about, some other specialized things that we're not going to talk about, and then there's the low-level routines. So as with all of these things that we've seen, these modules are interfaces to sophisticated routines, and in this case linear algebra is extremely important. It's a basis for an awful lot of algorithms, and so having very efficient, very powerful routines is important. And so there's really two sets of them. BLAS, which is basic linear algebra system. This is for doing all sorts of matrix, vector, multiplications, all sorts of things that you want to do, just manipulating matrices. And then LAPAC has a lot of these routines, like the solvers and all that. So we can get our hands on those if we want to. We can get our hands on the low-level routines. Again, not something that we're going to be interested in here, but it is available and does give us a lot of power. Okay, so for our purposes, we're interested in solving a system of equations, and that's what solve does. It solves the equation of the form ax equals b for x, exactly as we discussed. Okay. The generic format of this is we feed it a and b. A is an m by m matrix. Okay. It's a square matrix. That means it has the same number of rows and columns. And b is either an m, m component thing, like a vector of length m, the same as the array, or it can have any number of columns. So it has to have m rows, but it can have any number n of columns, again, as we discussed in class. And that's what we're going to solve for, all these right-hand sides of our equation. Okay. There's various other things that are in here. You can mostly read through them yourself, various optimization things. And there's also the ability to overwrite A and overwrite B. As we saw in class when we talked about Gaussian elimination, what did we do? Well, we were really manipulating rows of our matrix A and our vector B. That can be done in place. In other words, we can overwrite A and B as we go along doing that, and that's kind of what we were doing or thinking of doing as we were doing it in class. Okay. Alternatively, we can keep a separate copy of A and B and work in, make a copy of it and work in the copy to modify it. That's the default. So the default is to not overwrite these. If we were dealing with very large matrices, we're concerned about speed, about memory, then this would be the best thing to do, just to overwrite, okay, and lose our A's and B's. But if we're trying to solve a system, that's probably okay. So anyway, we're not going to worry about that. We're going to not work with problems where that matters, where we won't run into memory issues and whatnot. But it is there, and in general, if we were dealing with big problems, we would definitely want to use those. Okay. What does it return? Well, it returns the solution, x. So it returns either a vector, as we talked about and saw in class, or if we have a bunch of right-hand sides, it returns something of the same shape as what we put in. Okay. So let's go ahead and use this. Solve ax equals b. So we feed in our a and b, and we get back our vector of solutions exactly as we saw in class. So let's call that x. Okay. And what what we really should do is we should test to see whether this is a valid solution. Okay, that's the beauty of algebra. The beauty of algebra is we always know that we have the right answer because we can always plug our answer back in and see if it really works. So how do we do that? So our first thought might be, well, we want to calculate ax, so do a times x. Okay, that does not work. Ax is supposed to return a vector. That is clearly not a vector. In fact, what it's done is it's multiplied a, each column in A by one of these values. Okay, so multiply the first column by 0, the second column by -1, the third column by +1. Okay. This is the, let's call it annoyance or maybe even disadvantage of using these generic arrays when we're dealing with vectors and matrices. Okay, because multiplication isn't vector multiplication or matrix multiplication. It's component-wise multiplication. That type of behavior is typically what we want when we're dealing with generic arrays of data, for example. Okay, so this is generically good behavior. It's not so good when we were dealing with vectors and matrices, and this is one case where using a matrix object itself would be a little easier. Instead, we've got to do a little extra work. We have to use a special routine for doing this, and that's called dot. Okay, as the name suggests, it calculates the dot product of two arrays. They give a generic formula here, but really, for two-dimensional arrays, it's matrix multiplication. Okay, so if we have two-dimensional arrays that we feed in, it does matrix multiplication. Okay, if we feed in two one-dimensional arrays, it does the inner product, or what we typically call the dot product. So for our purposes, if we feed in a matrix and a vector, it's going to do the right type of multiplication. So again, it's probably best just to see that. So if we dot a and x together, we get back a vector as we should. In fact, we get back the vector that we expect. Right? Ax is supposed to equal b, so if I subtract off b, what do you know? We get the right answer. Okay, we get 0, so showing that this returned the correct thing. So that's a good thing to check. Well, that's it for solving. I mean, there's really not much more to it than that. Okay. We also saw that there were various LU things. So again, LU decomposition is something that we're going to talk a bit more about in class on Wednesday. But it's useful in the context of solving for systems of linear equations. Notice there's an LU solve here, which is what we're going to want to use. So let's start by talking a little about the LU decomposition. So again, we're going to talk about it a bit more in class, but we can see its behavior here. It computes what's called the pivoted LU decomposition. Okay, so P they call it the permutation matrix, but again, we talked about pivoting in the context of Gaussian elimination. That's what this is supposed to represent. Okay, the permutation matrix represents how we swap the rows of our matrix around. L and U then really are the key things, hence the name LU. L is a lower triangular matrix with unit values or ones along the diagonal, and U is an upper triangular matrix. Okay. Now we can be clever about how this P gets stored. It can be multiplied into L or whatnot, and that's what this permute L does. We're not going to worry about that. We can also overwrite again for memory and speed considerations if we were interested, but again, we're not going to do that. Okay, so what does it return? It returns P, which is the permutation matrix. It returns L, which is a lower triangular matrix. Notice that we aren't forced to feed it a square matrix, m by m. Okay, we can feed in an m by n array. Okay, and so then this will get the correct sizes for them. Again, probably the best thing to do is to look at an example. Hopefully that will make more sense. So here we go. So again, the first thing is a permutation matrix, which is just made up of zeros and 1. In fact, there should only be 1, 1 in each row. And this tells me how I'm going to swap the rows. Again, as we mentioned in class, to solve this problem with pivoting, really simple pivoting, we want to swap the second and third rows. And that's exactly what is represented here. The first row doesn't change, and these two get swapped. That's what this means. Here's L. L is a lower triangular matrix, so there's zeros up here, with ones along the diagonal, and so non-negligible or interesting values below that. And then U is an upper triangular matrix. 0's down here, the value's up here. Okay. So let's just solve this, or save these as things. So P, L, and U. Okay. And if we multiply all of these together, we should get A back. What does multiply them together mean? Just like we saw before, we have to do dot. Okay. So this will multiply P and L. Okay, well, it's not horribly interesting, but we can see that it really did swap. The last two rows got swapped in this. Okay. If we want to now multiply this into U, we need to use another dot. Okay. So this is where not using matrices starts to become really annoying, is we've got to start stringing all these dots together if we want to multiply lots of matrices. There are shorter hand ways of doing this, but not much shorter, and so this is perfectly good for us. So we see it returns a matrix as it should. In fact, it returns the matrix A, which we can verify by subtracting it, and so we see we get a matrix of all zeros. Well, okay, we've got these tiny values, but 10 to the minus 16 is numerical precision, and so that's equivalent to 0. So that's the LU factorization that's done for us. Okay. Well, that's great, but that's not immediately useful for solving. Okay. To solve a system, we want to use this somehow, and so there were a couple of other routines that did this for us. So one of them was there was something called LU factor. What does this do? Well, this also does the LU decomposition. Okay. In fact, exactly the same format, with one important difference. First, this one requires an m by m array, okay, because we're going to want to solve a system of equations. So we need this to be a square matrix. And it returns it in a different way. It returns something called LU and something called PIV. LU really is a combination of the L and U matrices, and PIV is a different way of representing how the rows get pivoted. Okay, different representation of the permutation matrix. This is done basically to conserve space, to store it in a way that's convenient for solving the system, linear system of equations, by the routine LU solve. So you can really think of LU factor as just setting up to solve a system of equations using LU solve. Well, so once again, let's look at what it does. Okay. Notice it returns much less information, or at least it stores the same information much more compactly. Again, this thing is LU, the first two-dimensional array here. We can see that because the upper part of this is U. Let's pull that out again, U. So notice U appears here. Okay. The lower part is L without the ones, because we don't really need the ones. We know there's ones there, so there's really no point in storing them. And so these three values here, 0.5 minus 0.3 and minus 0.04, are L. Okay, all stored in one matrix, so now we haven't wasted any space. And the permutation matrix is stored in this form. We really don't have to worry about the details. Okay. We don't have to worry about them because what we want to do is use this for solving a system of equations. And so we can do that, okay, AX equals B, given the LU factorization. So this has to have been done first, and it's passed in this thing called LU and PIV, and then there's B that we pass in. Again, other things. There's details about this transformation if we wanted to solve not just AX equals B, but A transpose or A adjoint, if that means anything to you, the Hermitian adjoint. We could do that. Again, for our purposes, don't need to worry about that. We're just going to solve AX equals B, and it's set up to do that. So this LU PIV is this tuple LU comma PIV, i.e. exactly the thing given to us by LU factor. So what we should probably do is go back, save this. I don't know, I'll call this LU decomp. Okay, that's the LU decomposition. Okay, it stores it again in a tuple, as we can see because the parentheses around it, exactly the format that's required. So now we can do LU solve. We feed in exactly that thing that was given to us, B, and lo and behold, we get the same answer back. Okay, that's the X that we found before. Okay. Now, doing all of this just to solve a single equation, a set of equations, is not so useful. The value of this is now that we've done this decomposition, we don't have to do it again. So if I change b in some way, I don't know, add 1 to it, okay, I don't have to redo the decomposition. I can just feed in the new b. Okay, divide b by 10. Okay, I can do this in any number of things that I want to do. I can take the exponential of b. Okay, and it will reuse what it had done before, the LU decomposition, and essentially just do, as we're going to discuss in class, what's necessary to solve the system, okay, which is far less work. And so that's the general advantage of having these decompositions, only having to do them once for each matrix, and then reusing them as need be. And again, other of the decompositions are useful for this too. Okay, so that gets us up to speed, at least on the tools for solving systems of equations and the various things that we can do with them. And so we'll explore more of that in the homework lab, and I guess a little bit in class.